Everyone. Thanks for joining us for Classiq workshop. We're excited to have everyone here and get acquainted with their tools and challenge. So please welcome Ron Cohen. He's the quantum software engineer at Classiq, a leading quantum computing company which provides end-to-end quantum software platform that utilizes the power of high-level functional modeling and enables the design, optimization, analysis, and execution of quantum algorithms. So he has worked on some pretty exciting research topics, like developing quantum algorithms such as amplitude estimation and methods to exponentially reduce circuit size. So during this workshop, he'll cover fundamental concepts of high-level functional design and then kind of deep dive into hands-on examples where you'll create kind of your own quantum algorithms during the workshop. It'll introduce some of the essential tools needed to approach their challenge, which is implementing an exponential quantum advantage algorithm using their platform in regards to achieving exponential quantum speedups in simulating coupled classical oscillators. So make sure to have a Jupyter notebook open to follow alongside. So now please welcome Ron.
Thank you so much, Jenny, for the introduction. So let me share my screen. This one. Can you see my screen?
Yes, we can see it.
Great. So put the participants at the site. Okay, perfect. So Zoom is not just to make a more comfort screen. Okay. So again, thank you for the introduction. If you wonder what is going on behind me, this is the API Smart Chain meeting. So I'm in a Classiq booth delivering from here. And I am here to tell you about Classiq in a practical way, to tell you about what we are doing and to give you the feeling of the what we are allowing our users to do while they develop quantum algorithms. So let me start with just briefly, what is Classiq? What are we doing? So it's an end-to-end quantum software development. My name is Ron. I'm a quantum application architect. I have a master's degree in electrical engineering in the field of quantum error correction and measurement-based. I work in Classiq for about 2 years. I have been in the R&D, developing in the library team, and then in execution on hardwares. And now I'm a quantum application architect, which means I work with users like you, and I'm telling them how they use the product. I learn the research, and I'm the guy for you. So that's about me. And what is Classiq? As I said, quantum software tool that enables you to design, optimize, analyze, and execute quantum algorithms. So that's what we do. And before I give you the introduction and motivation and history, I just want to make sure let's feel comfortable that you are set up and you can open. Try to please type everyone platform.classiq.io. And over there, I will be happy that you can sign up. And also in your Jupyter notebooks, we will install Classiq. So make like a smooth workshop. And then I will give you the brief about the product and what we are doing. So once you go to platform.classiq.io, there is a short sign up process. You can sign up with your Google account. I will give you like 2 minutes for that. And at the same time, as Classiq allows you a graphical interface, it also allows you a Python SDK package. So open your Jupyter notebook. You could do pip install -u Classiq to install it in the environment. If there are any problems, no worries. Don't tell me about them now. We will do it while we start the workshop, but just to try to start as smooth as possible. You could do the pip install also in a Jupyter Notebook cell with the, like start you do the Shift 1 sign. Another last minute. Okay, so I would continue. Don't worry if you didn't have the time to complete the process. We will do it later. I want to give you the brief, and we want to start the workshop, and I will help you with this later. Just let's look at the history. When we talk about quantum computers, we thought, okay, let's learn from the history that 6 years ago when they wanted to develop classical computers, which are really a very big and complex with billions of transistors, etc. It's a complex job, and actually, this is the era where quantum computers are today, because when you write in a gate level language, so you have qubit by qubit, gate by gate, so many operations that you have to do, and we want to abstract it. So we learned from the CAD, if you know the approach of how do you do electronic design automation. We said, okay, so to develop such things, you define blocks which are very in the low level, and then you define another block which is a bit higher level that contain a few different blocks, and then it's come higher and higher. So a chip design which contains billions of transistors can be a good model like to how to do it in a quantum algorithm, and this is our motivation. Also, like in the QIP conference not long time ago, there was a research that talked about the importance of doing abstraction and a high-level computing, because it's really not practical to do such a very low level and so many gates. So how do we do it? Imagine any language, high-level language that you know, C++, Python, MATLAB, whatever, and think about the, let me take my pen. Think about this simple calculation, multiplication and addition. There are so many machine-level operations behind this one, and in Classiq, we are allowing to do it with just one line. We also think about Q numbers. As you can see, take the highlighter. You can see the QNum type, which actually composed of many qubits. It can be also fractional number. It can be signed or unsigned. So we allocate space for X. And we could also do the if operator, for example. If you think about if in quantum, when you do a control operation like controlled not, so this is an if operator actually, because it's the operation is depend on the value of in a quantum way of another register. But I don't want to do just one qubit. So maybe I want to do, and this is what we do in Classiq. You can put any Boolean expression here inside, like if X is bigger than minus 3.75. And there's the repeat command. So everything you see here is a high-level modeling language to do, and this is very similar to the workshop you are about to do, high-level modeling. So things like, of course, doing QSVT, for example, or many other applications. We have a library of applications. So you can input it in the graphical interface that where you just signed up in a native language that's called QMod. You can input also in your Jupyter notebooks by doing import Classiq. And you could also give inputs as a graphical interface, just connecting the lines as a graphical CAD applications. So this is the high-level functional design. Now, let's take another example, like the Grover search algorithm. So in a Grover search, we could also do in a QMod native way. You can define an oracle in a high level. You could do it in the Jupyter Notebook, and you could do it in the graphical interface in a way that you could choose the Grover, and there's a built-in example as you can play with it later and see it. Now, once the user defined what he wants to do rather than how to do it, the implementation, he wants to optimize it because different functions have different implementations. The implementation might depend on the hardware. Different hardwares can have different implementation. And maybe I want an implementation that has shorter depths and bigger widths, or vice versa. Maybe I want an implementation that minimizes the number of CX gates count, for example. So this is how we allowed it. We let the user specify what he wants to optimize, and our engine is choosing the implementation for him, actually writing it. If he wants, he can write also the low level with Classiq. It's not a limitation. He can do both the high level and low level. But if you want to do high level, we automatically choose the optimized implementation for him by synthesizing the high level model. And you will practice it and hands-on very soon. Now, once it's synthesized, I can analyze, and I can analyze to see different implementation. Like those two circuits has the same functionality, but they do it in a different way. One is optimizing depths, and the other is optimizing widths. Because, for example, a multi-control NOT gate, you could do the same multi-control NOT, but with more auxiliaries or less auxiliaries, and just to save depths. Another interesting thing to mention here is that we do auto auxiliary management, because auxiliary starts from a 0 state. I can use it, but then I can uncompute it and reuse it again in another module. So once we finish, in this example, the Oracle op, you can see the auxiliaries here. After the Oracle op, it is released and it is ready to use for another block. So I can save qubits, maybe to shrink it into a simulator. Now, just to show you the analysis that is interactive, that I can zoom in and out, and I can zoom in and out, and I can see both the high level and the low level in an interactive way. So here's the Grover algorithm. I can zoom in, look inside. Here is the arithmetic. I can do addition. I can check if equal. All the arithmetic operations that are supported by the language are seen here in a visual way. Checking equality, for example. And that's it. You saw my screen, right? I did not share just the PowerPoint. Okay. So this is the analysis. So we had high-level model, we have optimization, we have visualization, and now we want to execute. So we can execute on a handy list of providers. It can be hardware, all IBM hardware, all Amazon Bracket hardware, Quantinuum, Rigetti, IonQ. Now we have also Alice and Bob. You have NVIDIA GPU simulator available for you. It's running on our cloud, and you can access it and to simulate 30 qubits rather than 25, if you like. And also with both in the graphical interface and also in the Python SDK. Once you execute, you can interactively see the histogram. And as you can see here, the histogram means that every state has a representation with qubits, like 0 and 1s, but I don't care about the qubits. I care that A equals 0. 0 maybe is 0, 0, 0 in binary, and B is 1, 1, but it's not 1, 1. It means 3. I don't care about the qubits. So again, the high-level formatting. This is the histogram, and of course, I can download the results as a file. I can download the circuit in QASM, in Q#. I didn't show you here, but here in this button, you can download in different formats. I can show you it later interactively. So we understood what, why, and how Classiq, and now let's talk about why functional building blocks. Just as a motivation, in the same conference, this guy said how to put into practice. But when you read a quantum algorithm paper, you identify primitives. So how do I implement these primitives? So I can tell you, for example, that 2 weeks ago, JP Morgan published an article that they, totally theoretical article that they simulated Brownian motion to simulate behavior of asset price. And they had exponent and cosinus and addition and multiplication. It was totally theoretical because they didn't have the way to do it. And in 2 days, I learned the language because it had changes, pretty new, and also implemented the article. So this guy said that you must have some way to do things in high level. Don't count the number of quantum algorithms you know, and focus on the algorithms primitives you learn. So that's the motivation for it, to get a toolbox. You go with it, you have a toolbox to implement whatever you like, and you can do both the high level and low level. So enough to hear me talking. Let's do a hand-on workshop. So first thing you can do, join the Classiq Slack channel. It could be just, I can write this link, then we can communicate easily inside the Slack channel. So I will give you a minute to do it. Just type. The workshop will be also inside the Slack channel, so you have to do it in order to participate in the workshop. And then once you are inside the Slack, look for the general channel. I have just published like 15 minutes ago a QRISE workshop, and I sent the, can show you. Sorry.
Don't go much deeper than that.
I send it now. So you can download here the file. This is a Jupyter notebook. So if some of you didn't have the chance to copy the link, please let me know. But in a while, I will show you how the notebooks look like. So you download here in this button. You open it in any Jupyter Lab environment that you are working with. And then once you're here, you also have the installation of Classiq if you haven't done it yet. If those, for those of you who did not write in Jupyter yet, it's like exactly like Python, but you run it cell by cell. So if you do Shift Enter, so it's running the cell. So the first cell install Classiq. So we're gonna make the workshop like in a dependent way. We will not have enough time to do everything, and we'll be able to continue by yourself once we finish. But the first parts we do together. We make some stops every time. Feel free to continue in your own pace, and we will go through an examples. You can ask me anything. I will be available here. I will do stops once in a while to show you what we are doing. And feel free to ask questions. Just can speak and I will hear you, and you can ask questions. Feel free to interrupt. I will try to be quiet in the other time. And once you install Classiq, you import and you do authentication. So once you do authentication, the window of logging in of the browser will open up by itself, like this. So since I'm already logged in, the browser did not open, but you log in with the same account that you just sign in. And then here you import all the functionalities. Of course, that you could import function by function, but to make it easy here, we import all the function. And I will tell you that there is a cheat sheet below for how to initialize a new register, how to allocate, how to do operations like repeat, how to do control. with examples.
You don't know how it works. You can't change the pills the way that you can a pill system.
So once you have done all of this, so now it's independent work, and feel free to ask. We will start with a warm-up. So in this warm-up, we prepare the minor state, a very simple low-level programming. And feel free to ask questions. This is just a warm-up, and I will show everyone the solution in a few minutes. I would also say that we have the user guide. So everything that you want to look for once you are in the platform. Once you're inside the platform.classiq.io, so there's the button on the right upper corner, the user guide.
The more I'm looking at it, I'm like, oh, yeah. You're like, oh, that's connected to that. Sweet. We just needed a little bit more length to get it.
And there's the getting started, etc. And if you want to see the different functions that we have, so I will send the link for this one here with the documentation, everything inside. Of course, the other parts of the user guide contain application and examples and things like that. But the basic things that you need for this workshop is here. So I'm in the thread of the QRISE workshop. I'm sending the link for the documentation.
University project.
Okay.
So they big into optics, they buy optics there all the time. My God, they think that bring crystals on you. Like, what is wrong with this cube? What's wrong with this cube? It's the perfectly good cube.
I know. I did, before I did, grad.
Thank you, Jenny, for sending the links.
Are they actually undergrad students started Dear IRB.
Oh, no. I have a very sad accident to say I was the lab makeup manager for my laboratory, and one kid ended up getting a eye shot with the infrared.
Oh my
See, because he did the, is this like aligned? Like, oh, why would you do that? There's no RV in the infrared. You cannot see it. The laser is on. These things take it on.
I mean, the first thing I told my students, like now that I'm teaching up computer safety,
Okay, so let's do a synchronization on this one. So if you want to do a bell state, this is actually just preparing just one qubit state. So if we want to prepare the minus state, we know that if we apply the X gate and then Hadamard, X gate get me to 1, and then when I do Hadamard, so I get the 0 minus 1. So how do I do it with Classiq? We have X, which is a type of a qubit, and then I just apply X and Hadamard on X. And once in the main function, which is the main entry point for the entire algorithm, I do allocation for X to 1 qubit, and this is for the initialization. And then I call the function that I have just created. So I have the main, and now I have to create the model, which is actually like a string, like a text file that contains everything that I need to represent the high-level model. And the synthesis is giving me the quantum program, which contains the implementation that was chosen. So this function is actually calling the Classiq API. It's talking with the cloud, making the optimization, and returning the. This is the first time you call the Classiq API. The first time you need the token and the authentication. So I synthesize. And then once I show, so the browser of the IDE pops up with the analysis at the side. And oh, this is not this one. And here's my prepare minus state. Again, in a hierarchical way. With the data at the side, I can do also Azure Quantum Resource Estimator, if you like, error correction, and the program info, and the information about the transpiled program info. If we choose a backend, which we don't do in this workshop, you will see actually the native gates of the hardware that you chose. So this is regarding this. Any questions so far before we continue? I will feel free to say you still want another minute to check it out.
Yeah, I think there was a question in the chat. They said that Classiq dot authenticate fails. Is there some registering they have to do?
Oh, sure. Yeah, sure. So feel free to interrupt even before while I'm speaking. This is okay. So overwrite equal true. I'm not so reading the chat. I will try to, but feel free to speak out loud. Oh, you have to if you did not register yet. So once you're in platform.classiq.io, as I showed in the beginning. So you click let me log out. You click the sign up. And then you do the process. The best is to sign up with Google. This is faster.
I don't misheard. Besides that, I don't get the focus on anyone there. Everybody calls it.
Any more questions here?
No, I
Hey. So I'm still seeing the same issue. Import Classiq, I think that is going through. Classiq dot authenticate override is equals to true is what I need to give, right? Even if I do that, I am logged in, as in, but how, I am logged in the same window in the browser, but I get attribute error, closing or creating new connections as required and stuff like that.
Did the browser window pop up for you once you did the Classiq.authenticate?
No. Okay.
Did not?
Maybe some pop-up would have come. That's what you're saying.
And the import Classiq works fine, right?
Yes.
Did anyone else have the same issue? Did you sign up to the platform?
Yeah. I signed up. Okay, fine. If no one else has this issue, let's probably move on. I'll try and figure out if there is something wrong at my end. I'll text you later separately.
Yeah, maybe I will try to help a few more. Like again, did you say that the window pop up for the login, or it did not?
No, it did not pop up. I'll do one thing. I'll join in Zoom from the laptop in which I'm working on. Maybe I can share my screen. Maybe if
Yeah, you can
Yeah.
share your screen. Let's have a look.
Thank you.
yeah. Well, they go out and get it.
All right. I gotta be.
Meanwhile, the others feel free to move on to the next exercise of a uniform superposition, also like a warm-up exercise. And not long later, we will do the synchronization again.
Yeah, yeah. I am studying third level of high school students. Or at least I've been.
So I'm gonna proceed just for the time to make it efficient, and for those of you who keep trying like the installation, and don't worry, because this is a very self-guided workshop. So if you in this time you will not have the time to do everything, you can do it, and you can also ask me. It's like just send me a direct message. I will be available to help you with anything. In order to do uniform superposition, we want to apply Hadamard gate to each one of the qubits. So there is an operand that's called apply to all. So the apply to all operand. So there is the gate that we want to do, and there is the target, like what is the qubit that you want to do. And again, if you go to the documentation, you can see how it looks like. So you can search for the apply to all, apply to all. So we can take a look at an example with apply to all. So here you can see that I want to apply to all the X gate on which register? The register that is called state, which is array of qubits. So here we want to do the apply to all, of course, the Hadamard gate on this register. So I hope you don't mind if I do like this. I imagine that the solution should look like this. I want to apply all Hadamard to reg. Now inside the main, it's like before. You want to do to allocate, as you did before here, as we did for allocation of a qubit. So you want to allocate. Let's say I can allocate 2 qubits on X, but it doesn't know what X is. So as before, we have to tell that we want X to be an output of the type of this type. This is the type of X or a reg or whatever we want. So this would be reg. And then we want just to call it, to call the function we created before with reg. Let's look at more clean. So a uniform superposition, we want to apply all the H, and then to allocate a few qubits and create the model. So I do Shift Enter, I run it, and then I can synthesize and to show the Q program. Now, since I signed out, I have to authenticate. And here is the program, which is creating initial state superposition of all. This one will be useful later on. Great. So feel free to move in your own time to the next exercise. Now it's the arithmetic operation that we talked about. So there is an example here. In this example, we want to allocate 4 qubits, signed qubits, that like there is a qubit that say if they are negative or positive. And fraction digits, it can also be contain fraction. This time there is no fractions. And the register that we want to allocate for is X. So we want to allocate num. We are allocating a number. And we can do Hadamard transform on all X, like the initialization we did before. So we do X for everything. And a Y is a new register that is automatically created from X. It's the square of X plus 1. So there is a square here and addition in a quantum way. And this operator means Y is just now created. I don't need to first to allocate qubits for Y. This is automatically happening because I know how many qubits do I need for such an operation. So this is what the engine is doing automatically for you. And then we create the model. And once we have this model, we synthesize. So the engine will automatically choose the optimal implementation. And let's see which one did it choose.
But it's big compared to a lot of places. Like the town that I grew up in, still.
Please feel free to interrupt me for questions. So we allocated the number, Hadamard transform on all, and we did arithmetic. First, we have power, which is implemented like if you come to do it in a gate level, like how do I do power? So I don't know. Here is the power. Just do the power and Classiq do it for you, and you can explore and understand how it's implemented. And then once so the way we do it is QFT and QFT inverse. So we do the power actually, we do the multiplication on the phase space. This is one of the implementation. The engine could choose another one. It depends what we want to optimize, but this is what it chose. And then I don't want to do the addition. So I want to add the 1. And that in order to do addition, I can also do it with QFT. And there is also another implementation with Toffoli gates. So this is how it looks like. So I can now, I expand all, I can look at the entire circuit. I can navigate in the circuit. There is the navigation bar over here. So I can do things like that. I get inside easily. And I have this is a 11 qubits circuit. So that's it.
Okay.
About the arithmetic example and how we do it. Any questions for so far before the advanced arithmetic?
Okay. Yeah, I have. Yeah.
Okay, feel free to interrupt. No worries.
Who knows? Yeah.
I hope you are doing well there. Now to some advanced arithmetic. So here I have multiplication in a constant rather than multiplication in another quantum register. And this one is parametric. I want to calculate y equal ax plus b. So I do it in the same way with this capture operator that do automatic allocation. And A is a Q param. Its type is int. It is not it's not quantum register. It's like a constant, but still a multiplication in a constant in a quantum way. This is still a heavy circuit. Since A is parametric, I have to initialize it somewhere. Okay, I want to be A to be equal 2 and B equal 1. I have the register X, which is the input, and Y, which is the output. And then I can do allocation for X. So X is again a quantum register. And I do a superposition of all possible X's. And then I can call 2X plus 1 in a way which is parametric rather than straightforward numbers. And here again, in the same way, we can synthesize our model and get the program. Now let's do see how we do execution. So once we have a quantum program, we can execute it. So we have a job, we send it to execution. We could also, you can look at the user guide, how you can send it to a backend, to hardware, but the default is doing it on a simulator. And then I can open the job in the IDE. So here's the execution. So you see that for each of the x values, x equals 6, so y equal 2x plus 1, just as the linear functions that we've just done. It is bit string, but I don't care about the bit string. I only care about the fact that y equal 2x plus 1. I can also download the histogram as a CSV file, for example, and could do any analysis that I want to.
Are you? Me too. Well, for a couple more months. Yeah, yeah.
Okay.
Bang. Yeah.
So this is how we do execution. And we can also see the results not in a graphical way. We can also parse them. So this is the way to see that for any value of x, y equal 2x plus 1. So we see that, okay, this is correct. This is doing what we want to do. We executed and this worked as expected. Now it's your turn. Implement the same linear function, but now x is in the domain between 0 to 1 and represented by 4 qubits. Like x is a fractional now and not an integer. So the parameters a, b should be now floats, like a multiplication in a float with something which is fractional, where a is half and b is 1.5. So go ahead and we do the sync in a few minutes.
It's small. So you never. I always ask like, just you know, like you could be my cousin. That's why I was like,
Please feel free to let me know if I'm going too fast or too slow.
But that's fine.
I have no problem to change the pace. Anyway, okay. Notice you don't have to define linear func again. It's already defined. Oh, sorry. Now a and b are floats, so just change the type.
We have a question in the chat. Oh, sorry. Go on.
No, Jenny, I was about to say the same thing.
Oh, okay. So they ask, what does it mean to have a classical variable A and B? How do they differ from QNUM, etc. I think you're muted. Yeah. Sorry, Ron. I think you're muted.
Oh, sorry.
Yeah,
So
now
you
you're
don't,
good.
yeah, thank you. So we don't need quantum registers for A and B because they are parameters. And if you want to do such multiplication and addition, it doesn't must be in a way that initializes A to a quantum register. You can do it like if for QFT, for example. So you can do the addition in place, like in the phases. So it's a number. I don't need it's in a quantum way. It's not in a superposition of anything. It's just the parameters that tell me how to implement my function. But it's not a quantum register. In some implementation, it could be a quantum register with I initialize to a specific state, just X in the relevant X gate in the relevant places, but it will not be in a superposition, and then I can use it. But it's still a parameter. It's not necessary to have a register for it. And you ask, is there any hidden measurement or state collapse when we use them? No. So I would go over the solution of this one. So here they are defined with fractions, and I let x to have 4 fraction digits. So it means that the resolution of x is 2 to the power of minus 4. This is the resolution of x. And then I create the model, and you can do the show circuit and to see what was implemented. Now let's move on to the next thing. Let's do a controlled linear operation. So like maybe sometimes I want to do a 2x plus 1, but when another qubit is in a state of, depend on its state, if it's 0 or 1, maybe I want to do another calculation. So this is the control, and this is the usage in if. So take a few minutes, like independently read this one.
Okay, I gotta come back. My homegirl.
So the in-place linear attempt, we have to do, this is a linear function, but since we want to put it into another register, so it's like I can save a temporal variable and to put the result of the linear function into temp. And then I can take temp and put it into y with a linear XOR. Like you take CNOTs and I copy the values from temp to y. Let me show you how it looks in the circuit. Before we move to how do you do the actual if statement, so you can see here that I do the linear function, and then I use the XOR to copy the result into another register here, the y at the top. So now let's do a control logic. Let's say that there is a controller, which is a number, and for each values of the controller, I want to do a different A and B. So what I do is using the quantum if operator, which is taking this expression, and we have to check the controller value. For each layer in the repeat, which is also a new operator, I have here the index. So I can repeat, let's say that a.len is the length of, let's say this is the number. So let's say I repeat 5 times. So I is running from 0 to 4. And for each iteration, I do iteration that is depend on the value of y. So when controller equals 0, do this linear function. When controller equal 1, do another linear function with if. And then we can do the same thing. Just now we have a controller which sometimes is 0, sometimes it is 1. And for different values of the controller, I call this control logic to implement different values and to do different linear function. It's very nice to see how the program will look like in the visualizer, where you see different values of control to do different in place linear function. So here is the repeat. So the first round is I equals 0. And the controller, only when the controller value is 0, this is the empty dot, I want to do in place. But this in place is done with specific A and B. And this in place, when the controller equal 1, is done with another A and B, which is using this array. So there is the first A and B, and there is the second A and B. And we can prove ourselves this is correct by seeing that for different value of the controller, the formula is different. One time is 2x plus 1, and the other times is x plus 2. Make sure you feel comfortable for a moment. And please let me know about any questions before we talk about optimization of depths and widths. Okay. So now let's see how can we optimize widths or depths. We could do, as I said, we can do the same functionality with more qubits, less depths, or vice versa. So you let the engine know what you want to optimize. So you do constrain when the optimization parameter is widths. You could, of course, you can go inside constrain and to see the type of the optimization. Just, if you are in Mac, command click, and Windows is control click, and you have optimization parameter that can be widths, depths, or also 6 counts is possible in the user guide. And I synthesize the same model, but now QProg will be different from this one when I want to optimize for depths. So when I optimize for widths, I get 20 qubits and with these depths, but I can optimize depths and do the same functionality this way. And maybe also let's do the show, just to show the different QProg. And so the first one is 20 qubits, more qubits, or the same thing. If you open it inside it, you see that the multi-control X gates can be implemented with more auxiliaries. And this one is for bigger depths, smaller depths, and bigger widths. This one will be the one with the more auxiliaries usage. You see here, all of these are just auxiliaries that are used to shorten the depths. So there are a few more exercises that are developing and expanding what we said. I don't want to take your time, and you can do it independently. In purpose, I put it a little bit longer notebook, so you will have the chance to write by yourself. And I'm for any questions before we finish. I would love to help, and you could also approach me in Slack. Just write me a direct message, and also to all the community. The community in Slack is very active. The workers of Classiq are very responsive for bugs, for questions, for examples you have. You can share your code. And this workshop, the purpose of this workshop is it will be very useful for you in the hackathon you're about to have. So I think it's about to be in the chemistry field, which we also support. Here I showed you just arithmetic. but you could do also chemistry, like in a very short code to do Suzuki trotter and exponentiation of an Hamiltonian that you give in a very nice way. We optimize the depths of Suzuki trotter circuits in a factor of 10 when they are controlled, because we have some trick to do optimization and cancellation of gates. And that's it. I'm here for you. Thank you so much for the participants.
Call for questions. If not, also Ron is available in their Slack channel, both in Classiq and I think you joined our QRISE class as well? If not, I can send you the link again, but thanks. This seems like a really awesome tool. I think having the it forms your circuits and then also connects you to the hardware side, which is, I think, pretty cool. Thank you, Ron. And then if anyone has any questions, feel free to stay behind for a few minutes. But other than that, thanks for attending. Explore this notebook on your own, and hope you guys have a great time working on their challenge. Have a nice day, everyone.